Okay. Now, basically, the exercise we did with the harmonic oscillator was, first of all, we can create these operators that can create or destroy packages. And these packages we can describe as particles. Of course, the particles that we know in everyday life, they are moving around. I mean, these particles, they don't have to be, I don't know, fundamental particles like electrons or muons. If you are doing, I don't know, condensed matter physics, or if you are talking with any condensed matter physicist, they also sometimes talk about excitons, phonons, etc. I mean, these annihilation creation operators can also describe them. And especially if you are interested in condensed matter crystals, for example, you can just write down a field theory for such a crystal by taking your space as discrete. Now we will be starting with a discrete space. How can we write down these annihilation creation operators in such a discrete space? But if you like, you can also generalize it to... no, okay. Then we will take the continuum limit. Now, what I will imagine is, let's just take some space-time points. And let me just label them by I plus 1, and I minus 1, etc. Now, the analog of particle in a box or a finite volume normalization when you are doing quantum mechanics, you study the plane wave solutions. Well, the plane wave solutions are somewhat problematic because they are not normalizable, etc. So what you do is you just imagine the plane waves to be in a box, or you impose periodic boundary conditions, etc. If you like, you can do actually the same thing over here. So we have these i's. At each point I imagine a harmonic oscillator. Now, keep in mind that the Hamiltonian basically determines two things. One, the energies of the system, and two, how the system evolves in time. So all this information is encoded in the Hamiltonian. So let's say if I put a particle in the position I, that particle might have some energy. In relativistic mechanics, for example, all the massive particles have their rest mass energies. So just having the particle, even if they don't have any kinetic energy, etc., they will still have an energy. So let's say that if I have some particle on the I side, each one of them will have an energy. Let's just call it epsilon I for the time being. So this just tells me how much energy, no, the HI is just this one. Of course, the energy expression can be more complicated. The energy need not increase by the number of particles. If the particles, for example, they are interacting with each other, you can end up having terms such as proportional to AI dagger AI, squared, etc. But just as a simple example, I will just ignore that. I am just looking for a theory in a simple theory in 1 plus 1 dimension. Later on, we will be considering also more complicated theories. So this epsilon I is the energy each particle has at the point I. Then the total Hamiltonian of my system will be sum of these. So I have, now if I have particles at different points, I just sum their energies. Still, this is not a system which moves. I want motion. So the simplest case I can imagine is I can just add a term. For example, this term might annihilate a particle at the point I and create a particle at the point I plus 1. Or, not or, it should be, the Hamiltonian should be Hermitian. Well, let's just add the Hermitian conjugate. So it annihilates a particle at the point I plus 1 and creates a particle at the point AI. Well, of course, these two terms need not have the same coefficient. One can have a coefficient, let's say lambda I, the other one can have a coefficient lambda I star, sum over all I. Again, I repeat, you can write more complicated terms over here. I mean, since we are just inventing our theory, why should the particle just jump to the next point? Maybe it jumps at a further point. You can add terms like AI plus 2 dagger. It just jumps 2 spaces. But as I said, I will just, for the time being at least, I will just keep my theory simple. Now this theory describes a system of particles that can just jump from one point to the other point. But that is what we call motion. Let's try to solve this system. Again, I will make lots of simplifications. Let's just say this is epsilon AI dagger AI plus all the lambdas, let's just assume them to be equal, lambda AI plus 1 dagger AI plus AI dagger AI plus 1. Well, what are the energy eigenvalues of this system? Well, I will make I will put this system in a box with periodic boundary conditions. So I will assume that AI plus n is actually AI. Okay, that is one assumption I will make. Eventually, I will take the limit. N goes to infinity, so that I actually have an infinite one dimension, and my particles are will be moving in that one dimension. And okay, so let's try to solve this. Now, first of all, I will define an operator, a different operator. Let me call that AK. This will be equal to sum of e to the power I kn an, and summing over all n. Oh, by the way, before continuing, I will also okay, let me also mention one more operator. Now, as we said in the last lecture, quantization basically means imposing the commutation relation between P and Q. Now, or imposing the commutation relation between A and A dagger. And in the previous case, we had just a single set of annihilation and creation operators, and they satisfy the quantization condition that this was equal to -1. Now I have many, now this is +1, sorry. A dagger is +1. Now I have many of them. At each site I have a different one. But, well, they are just different points, different particles. They will not be influencing each other. So now I have these AI and AI daggers, AJ daggers. If I and J are different, then these operators are completely different, so they commute with each other. If I and J are the same, then their commutator should be 1. So this commutator is just Kronecker delta Ij. So if you want to stick with the harmonic oscillator analogy, now here basically I have a harmonic oscillator at every point, but since these are different harmonic oscillators, their position and momentum of different harmonic oscillators, they just commute with each other. And all the other commutators are 0. Now let's see how does this AK commutes with my Hamiltonian. Well, let me put a minus sign. No, this is plus. Okay. Hamiltonian commutator with AK. Well, I know what my Hamiltonian is. In my Hamiltonian, there is a sum over I, sum over different sites. In this A operator, there is a sum over n. By the way, you should just realize that this is nothing but a discrete Fourier transform. Initially, I have a system which can move, which has translation invariance. So it can be diagonalized. Its eigenvalues are momentum eigenstates, which are obtained by just Fourier transform. That's why I'm making up that operator AK. It will probably solve my solution, my problem. Okay, sum over I and n. The commutator of epsilon AI dagger AI plus lambda AI plus 1 dagger AI plus lambda AI dagger AI plus 1, and there is the e to power I k n an, which is equal to the sum over I and n's e to power I k n AI dagger AI with an plus lambda AI plus 1 dagger AI an plus lambda AI dagger AI plus 1 an. Well, these annihilation operators themselves, they commute with each other. So I can just take them out of that commutation relation sign. AI dagger an AI plus lambda AI plus 1 dagger an AI plus lambda AI dagger an AI plus 1. Now let's continue. Now this is nothing but minus Kronecker delta IN. This is minus Kronecker delta I plus 1n, and this is Kronecker delta IN. Well, I can use this Kronecker deltas to sum over i's. So it leaves me sum over n e to power I k n. No, this is also minus. Well, here this Kronecker delta just tells me that only when I'm summing over I, only the term I is equal to n survives an plus there I have missed an epsilon. Minus epsilon an plus here I have minus lambda. Well, this tells me that only the I is equal to n minus 1 term survives, n minus 1. And here in the last term, again, only the I is equal to n term survives, so minus lambda an plus 1. Which is equal to n. Let me just write down the expression. Well, this is a sum either around the circle with periodic boundary conditions, or if you take the infinite capital N limit along a line. So the idea is if you just shift n by 1, plus 1 or minus 1, you are allowed to do that. The limits of that summation doesn't change. But in this term, I will shift n by plus 1, so that that operator becomes an. But you see, it is multiplied by e to power I k n. I'm shifting n by 1, so I'm also multiplying that term by e to power I k. In the last term, I'm shifting n by minus 1, so this becomes an. I'm replacing n by n minus 1. So there is an e to power I k n over there. So from that I get an additional factor of minus I k. So I have h a k is equal to, well, let me just take the minus sign out. And then I have sum over n e to power I k n well, an is common. I take it out. What remains inside is independent of n, so I can take it out of the summation. So I have epsilon plus lambda e to power ik plus lambda e to power minus ik. Or h commutator with ak is actually equal to minus epsilon plus 2 lambda cosine k times ak. Sorry. But we had already seen this commutation relation and studied what it means. So HAK, this commutator, this tells me that AK acting on any state with energy epsilon will give me a state whose energy is no, not epsilon. Let's use the capital E. E minus epsilon plus 2 lambda cosine k. And well, you can do the same thing with the dagger. So H, AK dagger, E plus epsilon plus 2 lambda cosine k, AK dagger E. So this just tells me that I actually solved the energy eigenvalues. The states of definite energy will be AK dagger to the power nk multiplied over k. But let's look at what AK is. AK we had defined this AK, or AK dagger is e to power minus ikn an. As I said, this is just a plane wave solution. I can invert this if you like. An dagger well, with certain factors, normalization factors, which I'm leaving aside. So if let's look at the state AK dagger 0. This is actually sum over e to power minus ikn. An dagger 0. And keep in mind what this is. This is a single energy packet at the position n. If you ask me, okay, what is the amplitude of observing in this state? What is the amplitude for observing a particle at the point n? I would just say, well, the amplitude is e to the power minus ikn, which is the wave function. So we started with a zero-dimensional field theory. Now we have a theory of one-dimensional non-interacting particles. The solutions are plane waves. They are just free to move and nothing happens to them. It's not much interesting, but at least for the time being, it's a simple demonstration of what we are actually doing in quantum field theory. Now, to this, we will add the interactions and the symmetries of the problem, of the system that we are trying to understand. Now, let's take the continuum limit of this problem. What does it look like in the continuum limit? Well, this was the Hamiltonian we had. Well, I will modify it slightly. I mean, you can do the same thing with this Hamiltonian, but especially when you are trying to go to the Lagrangian, it becomes complicated. To have a Hamiltonian which will have a simpler Lagrangian, let me just take the Hamiltonian. And take this second Hamiltonian. It still contains these terms of the previous Hamiltonian. It just has some additional terms. You see, in the initial Hamiltonian, we had this term, which, I mean, if you interpret the Hamiltonian as a time evolution, it annihilates one package at the point, this term over here, annihilates a package at the site I and creates a package at the site I. So it basically conserves the number of packages we have in our system. Or we had these terms, which annihilated a package at some point and created another package at the nearby point. Again, the second term, the term proportional to lambda, it also conserved the number of packages I had. So it was easier to solve. Now the second Hamiltonian, it contains such terms. For example, this term plus this product is actually what we have in the previous Lagrangian. But now we have these additional terms, this times this, and which basically, as time evolves, two packages just disappear, poof. Or these terms. Again, two packages, they just disappear. No, in this case, two packages, they can just appear out of nothing. But this will turn out to be easier to obtain the Lagrangian of. So that's why I'm just switching the Lagrangian, Hamiltonians. Okay, let's take the continuum limit. Now, the first problem we will have in taking the continuum limit is, keep in mind this I goes from minus infinity, if you like, to -5, -4, -3, -1, 0, 1, 2, 3, etc. Integers. Now, in the continuum case, I mean, summation will not have any meaning. And labeling points by their number, here I just gave us their number in the order. It won't have any meaning. So what we will do is, I will define the position of the points. So if x is equal to, let's say, I times L. Now, what is this L? Well, I had these points. I will be assuming that they are separated by a distance L. If x is I times L, then AI will be phi I times, no, there's no I, phi of x. So essentially at every space-time point I'm assigning an operator. And since space-time points, they are not countable, I cannot just count them one by one. So that's why I'm changing my label. Now let's start with, and what else will be is, I will have summations over I. Well, this I can write as summations over I times delta I. Delta I is just the change in I in successive terms. It's just one. But this is also the same thing as the change in x divided by L, which is, when I take the limit as the change in x as I increase I, when L goes to 0, that's the continuum limit, I'm just take the separation between 2 points to go to 0. And this will eventually go to this integral dx with the 1 over L. Now let's see what this epsilon is. Right. Let's just imagine we have a state in which at every site we have a single particle. And let's just ignore the lambda prime term for the time being. If we ignore the lambda prime term, then epsilon prime will be the energy at each site. So epsilon prime over lambda, L, is the energy per unit length along this one-dimensional system. I will keep this density constant as I take the limit L goes to 0. I will just call this, let me just call it epsilon tilde, finite constant. So as L goes to 0, I'm also taking the limit epsilon prime goes to 0, such that epsilon prime over L goes to a finite number. It will be the energy density. That's something I want, finite. Let's see what we will do with lambda in a moment. Well, let's make these changes. And on the way, we will see what kind of problems we will have, and we will see how we can solve those problems. Well, this will be equal to epsilon prime is still summed over I, is phi dagger at the point IL. This is phi at the point IL, plus lambda prime. Well, this is phi dagger at the point IL plus L. This is plus phi at the point IL, multiplied with phi dagger at the point IL plus phi at the point IL. Well, one thing I can do is I can just take the limit as L goes to 0 and replace phi dagger, phi and phi daggers by phi x. But if I do that, I will be missing a crucial point. You see, this operator over here should be the product of operators at different points. If I take the L go to 0 limit straight away, then that term just becomes the product of operators at the same point. There's no way I can distinguish that second line with the first line. So that's why I will not just take the limit straight away, but what I will do is this one. Plus lambda prime over 2 phi dagger IL plus 1 plus phi of IL, no, not 1, IL minus phi dagger IL minus phi IL. All of this thing squared. And here I have a minus sign. Now, when I take the square of this thing, well, I get an extra term, phi dagger IL plus L. Now, here there is an IL. Plus phi of IL plus L squared minus another additional term squared. Well, basically, when I take the square of this thing, there is this term squared. I am subtracting it. There is this term squared. I'm also subtracting that one. There is minus twice the product of those two terms. That is the term that I want over there. So that's why I have the minus lambda prime over 2. Now let's see what we will do. This is equal to epsilon prime I phi plus IL. Well, let me just switch to x. Well, there's a sum over x, phi dagger x, phi of x, minus lambda prime over 2. Well, here, you see, in that first term, I have phi plus IL plus L minus phi dagger L. Let me divide by L and multiply by L. But this term, this piece, in the limit L goes to 0, it just becomes the derivative. Derivative with respect to position. So that is why I made this one. So the lesson we learn over here is whenever you say a derivative, it just contains nearby points. It's not we are actually taking the local limit, but still the derivative terms couple nearby points. That's the lesson you should keep in mind whenever you see a derivative. Well, let's see what we had over there. We have sum over x. There is a square, so there is an L squared derivative of phi dagger plus phi. All of this thing squared. Minus, well, the other piece, there is nothing we do about that. There is just a product of operators at the same point. So I just take the limit, phi dagger x plus phi of x squared. But keep in mind this term, the second line and the third line, they basically contribute the same, because they are just they differ by a shift in I by 1. But the shift doesn't really change anything. So I have a factor 2. Which is, well, let me rewrite it. Minus lambda prime over 2 x lambda prime times L over 2 of derivative of phi dagger plus phi times L, another factor L over here. Here I have epsilon prime over L multiplied by L. This whole thing squared. And then I have plus lambda prime L summed over x phi dagger of x plus phi of x squared. Lambda prime L. Here there's a, no, let's just keep it lambda prime. Now we need to take the continuum limit. Well, I will do one more thing which I don't... okay. Well, okay, there's one problem that I see over here, this term. You see, this summation over x multiplied by L in the continuum limit, it will give me the integral. So it becomes the integral over x. Here, this whole thing I defined as epsilon tilde. This thing, let me also define by lambda tilde. I have epsilon tilde phi dagger x phi of x. Let me call this minus lambda tilde. Plus lambda tilde over 2 derivative of phi dagger plus phi squared. This term is what I don't really like. You see, I'm taking the limit L goes to 0 on one hand. So lambda prime times L should be finite if I want the second term over there. So this term, lambda prime goes to 0. Lambda prime should diverge in that limit. But if lambda prime diverges in that limit, here if I do this more or less the same trick, I should multiply by L and divide by L. Oh, okay. I know what the problem is. Okay. So I made one mistake. Well, this identification itself is kind of problematic. And the reason why it is problematic is this one. I identified this as phi of x. But keep in mind, a j dagger, we had called this as Kronecker delta ij. If I make this identification over here, then this just means that phi x, phi y is Kronecker delta ij. No, Kronecker delta xy. Well, Kronecker delta itself is meaningless for continuous variables. So we cannot really do this identification. But what I can do, now you see, what this also means is if I sum over all I, ai, aj dagger will be 1. I still would like to keep that identity when I go to the continuum limit. But the way to do that is this commutator, well, you see, this summation over I will go to an integral over dx. So this thing in the continuum limit will go to phi x, phi y, phi dagger y. This should be 1. But that already tells me that this commutator should actually be proportional to Kronecker delta x minus y. Now, if I make this identification, it just doesn't work. You see, what is the definition of the Kronecker delta? It is 0 if the arguments are different, if the argument is non-zero, and if it is infinite if the arguments is 0. So I should actually obtain not Kronecker delta xy, but Kronecker delta xy over L as L goes to 0. So that it diverges. But that tells me that the identification of the annihilation and creation operators is not really ai, is not really phi of x, but ai is 1 over square root of L of phi of x. Now, why 1 over L, but not 1 over L squared? Why 1 over square root of L? Okay, why should this be 1 over L, but not 1 over L squared? That's the question. Let's keep it there for the time being. Because I suspect that AI should be just 1 over L. So this should be 1 over L squared. Or let's just look at the dimensions. Now, here I want something that will go to Kronecker delta x minus y in the continuum limit. Okay, this has dimensions of 1 over length. So yes, that should be 1 over L, not L squared. Otherwise, dimensionally, it will be wrong. Okay, so let me correct my derivation over here. So here I have a 1 over square root of L. So what changes in these derivations? Well, here I get additional, there is a 1 over L over here already. Here there is an additional factor of L already. So from these I get 1 over square root of L. From these I get 1 over square root of L. So there is 1 over 2 L's over there. This derivative is correct. So here I already have a factor of 1 over L. Here lambda prime is divided by L. So now let me just rewrite this expression. So this is already epsilon prime over L squared summed over x times L of phi dagger of x, phi of x. Minus lambda prime over 2L, lambda prime over 2 sum over x of L derivative of phi dagger of x plus phi of x squared plus lambda prime over L sum over x phi dagger of x plus. Okay, still the problem still remains. Now these become just integrals. So this is our epsilon tilde. Lambda prime is just, lambda tilde is just lambda prime. Minus lambda prime, yes. Well, this term is a question mark. Okay, I will ignore it. Now, okay. The problem over there is when I take the limit L goes to 0. So you see here there will be a sum over x L divided by L squared. So lambda prime, I want this term lambda prime. So lambda prime does not go to 0. So as L goes to 0, this term diverges. So that's a term that I don't want to have.
You also change the definition of E tilde, right? You said E tilde, E prime divided by L squared is E tilde, right?
Yes, epsilon prime over L squared is now our E tilde.
It's no longer the density, is it?
You're right, it's no longer a density. Okay, let me check these definitions once more. But the basic idea is more or less this one. So you have the annihilation creation operators. In the continuum limit, we replace them by some kind of a function, operator valued function. Now there is this problem over here, which we should address in taking the continuum limit. But for the time being, let's just ignore the problem. And then hopefully next week I will have the answer for you. So this is, let's say, our new Hamiltonian. So Hamiltonian is just now the integral of something. So that integral over the whole space, that is usually called the density. So this is the Hamiltonian density. Now let's obtain our Lagrangian. We have the Hamiltonian, but not the Hamiltonian density, not the Lagrangian yet. Now, how do we go from the Hamiltonian to the Lagrangian? Well, let's just remember our harmonic oscillator case. You see, in the harmonic oscillator case, what we had was we had defined the A operator. The real part of the A operator was actually our position, and the imaginary part of the A operator was actually the momentum, proportional to the momentum. So the quantization condition, Px is equal to minus I h bar, is actually the same thing as A dagger is equal to I h bar. Now instead of a dagger, we have phi and phi dagger. And their commutator is, no, this is just 1, sorry. And now xy, this is Kronecker delta x minus y. So let's see what this means for the real part of phi and the imaginary part of phi. Let's say phi of x is equal to phi 1 of x plus I phi 2 of x. Phi 1 dagger is equal to phi 1 and phi 2 dagger is equal to phi 2. They are analogues of the real and the imaginary parts of phi. Well, let's see phi 1 of x, phi 2 of x. Let's look at their commutator. This is equal to phi 1 is phi plus phi dagger divided by 2. And phi 2 is phi minus phi dagger divided by 2i. So this is equal to 1 over 4i. Well, phi x and phi y, they just commute. They are both annihilation operators. And so I have minus the commutator of phi x and phi dagger y plus the commutator of phi dagger of x and phi of y. So this is equal to 1 over 4i. Well, the first one is Kronecker delta x minus y. The second one is also Kronecker delta, let's say y minus x, but they are the same thing. So this is 1 over 2i Kronecker delta x minus y. Well, this is just like the commutator of p and x. Well, there's this extra factor of 1 over 2, which we should somehow get rid of. Well, we can get rid of them by, let's say, by adding here, by just redefining. Let me redefine phi 1 of x as square root of 2 phi 1 of x, and phi 2 of x is equal to square root of 2 of phi 2 of x. So this gives me that phi 1 of x, phi 2 of x is actually equal to there's an additional factor of 2 now, that cancels 2 minus I Kronecker delta x minus y. Which is analogous to px is equal to minus I. So let's see if I made a mistake somewhere. So I'm looking at, so this is how I define the phi's. These are the real and imaginary parts. Phi 1 is phi plus phi dagger divided by 2, and phi 2 is 1 over 2i phi minus phi dagger. Now here I have 1 over 2, 1 over 2i, so that is 1 over 4i. Oh, sorry, here I have, okay, so here is a plus. There's a minus sign over here, which I forgot. So there's a minus sign over here. There's a plus. This is a plus. So it is the commutator of not p of x, but x and p. So this is plus, so which is analogous to x and p. Well, which basically tells me that I can identify phi1 of x with the generalized coordinate and phi2 of x with the conjugate generalized momentum. Now I can go to the, once I identified my generalized coordinates and momenta, I can go to the Lagrangian. Keep in mind the Lagrangian was sum over I, pi, qi dot minus the Hamiltonian, which in the continuum limit it will become dx phi pr phi 2 and qr phi 1 minus the Hamiltonian. Of course, there is one more step I have to do. I have to express p in terms of q dot. Phi 2 in terms of phi 1 dot. Of course, since now I'm talking about the time derivatives of operators, you should understand that we are in the Heisenberg picture, where the operators are time dependent now. Well, in the Heisenberg picture, what is phi 1 dot? H of commutator with phi 1 of x. Well, let me just use the y over here. And the overall factor is? Well, I will ignore the h bars. I'm not ignoring them. H bar is just 1. I'm not using meters or kilograms as my units. I'm using some other units in which h bar is 1. Is it minus or plus? It should be minus. Well, we know what h is, at least this much. This was our Hamiltonian. So phi 1 dot of y will be minus I, commutator of this with phi 1 of y. And, okay, so, okay. Now, first, I should better express my Hamiltonian in terms of phi 1 and phi 2. You see, this was the, okay, this is my Hamiltonian. Which is dx epsilon tilde. Now, capital phi, remember our definitions. Capital phi was, okay, these are the definitions we had. And which is square root of 2, 1 over square root of 2 phi 1 plus I phi 2. Hangi ders için geldin? Okay, so let's just continue. One over 2 phi 1 squared plus phi 2 squared plus lambda tilde over 2 square root of 2 no, over 4. Phi dagger plus phi is just square root of 2 of this phi 1. Square, phi dagger plus phi is square root of 2 of phi 1. So it cancels this 2 over here. So here I have the derivative of phi 1 squared. Well, in fact, this is why I insisted on using that weird combination to start with. Phi 1 was my generalized coordinate. I don't want the derivative of my momentum. So let's come to the phi 1 dot. This was minus I h phi 1. Well, the only thing it doesn't commute with, you see, it commutes with phi 1 squared. It will commute with the derivative of phi 1 squared. The only thing it will not commute with is phi 2. So this is actually equal to minus I epsilon tilde over 2 dx phi 2 squared at the point x with phi 1 of y. So I can use the commutation rules. This is dx phi 2 of x is the commutator of a product with a single operator, phi 2 of x, phi 1 of y, plus commutator of phi 2 of x, phi 1 of y, phi 2 of x. Well, this is, you remember, minus I Dirac delta x minus y. This is phi 2 and phi 1. Remember, we calculated it. Phi 1 and phi 2 gives plus I Dirac delta. So here I have phi 2, phi 1 commutator. This is minus I times Dirac delta. So phi 1 dot is minus epsilon tilde phi 2 of y. You see, these two terms basically give me the same result. So I cancel this 2. From both terms I have a minus I. There's a minus I over here. That is this minus over here. And Dirac delta x minus y, I can just use it to calculate the x integral. It will just give me the phi 2 of y here and phi 2 of y over there. So now I know what my momentum is. Phi 2 of y is actually minus 1 over epsilon tilde phi 1 of that. There's probably a sign mistake somewhere, but let's continue. Okay, now I can write my Lagrangian, which was dx. Phi 2 is my momentum. My momentum is minus 1 over epsilon tilde phi 1 dot times phi, my coordinate is phi 1 dot, minus my Hamiltonian. My Hamiltonian is the integral over h of these terms. Which is dx minus 1 over epsilon tilde phi 1 dot squared minus dx epsilon tilde over 2 phi 1 squared plus 1 over 2 epsilon tilde phi 1 dot squared plus inside lambda tilde derivative of phi 1 squared. Okay, here there's a sign mistake. This should be plus. So let's see if we can easily define it. Are you sure that this is a minus sign? You see, the operator in the Heisenberg picture is the operator e to power IHT or I think this was minus I ht.
That was plus, second one was minus.
The second one was plus, right?
No.
The first one is plus.
Here.
The second one is minus. What is the time evolution in Schrödinger picture? E to power minus I ht. Okay, so this is minus, this is, here we have the plus sign. So if we take the derivative of this plus sign, so this is plus. So this is plus, this is plus. Here I have a plus sign over there. This is a plus sign. So this is a plus sign, this is a plus sign. Okay, fine. So my Lagrangian is now dx 1 over 2 epsilon tilde phi 1 dot squared minus lambda tilde derivative of phi 1 squared and minus 1 over minus epsilon tilde over 2 phi 1 squared. Now let me make one more redefinition, a couple of more redefinitions. Let me define some new field. Let's give it a name. Psi. Okay. And I will call phi 1 over square root of epsilon tilde as my new field. Well, let me just call it eta. So phi 1 will be actually square root of epsilon tilde eta. I will define another constant c to be c over 2 to be epsilon tilde lambda tilde. And I will define another constant m to be epsilon tilde squared. M squared to be epsilon tilde squared. So why did I make these definitions? My Lagrangian now looks like this. You see, here I have phi 1 squared. It brings two factors of epsilon tilde, so there's no coefficient. The coefficient in front of eta dot is just epsilon. It's just 1 over 2. Now this is c squared over 2. Now the coefficient in the second term is c squared over 2, derivative of eta squared. And then I have minus m squared eta squared. Now this is called the Klein-Gordon Lagrangian. We will see that it actually describes a field with a mass m. This is the mass of the particle. This is the speed of light in that space. In this case, it will be a speed of the wave. So that's why I made all these mumbo jumbo about redefining the fields. And just like I have been working with units in which h bar is equal to 1, I will also choose the units c is equal to 1. Now, a couple of things to keep in mind over here. You see, here we had seen that this lambda term is the term that is actually responsible for the motion of the particle. If lambda term is not there, then the particle is not moving. It doesn't have any dynamics. Now that lambda term, as we carried it along, it became this term, or the derivative term. If there is no position derivatives of our fields, then it cannot describe particles that are moving around. So that is important to have those derivative terms. And what else we have? The other terms are somewhat complicated. For example, if you look at this mass term, mass was due to this epsilon tilde. But if you remember what we defined epsilon tilde to start with, or epsilon, we called epsilon to be the energy change in the system if we just add one particle to the system, ignoring the interactions and the motion, etc., ignoring the kinetic energy of the particle. If we create this particle, just its existence increases the energy of the system. Well, that is what we call the mass of a particle. If you just create a particle with minimum energy, it still increases the energy of the system by its mass energy. And okay, any questions up to here? By the way, this is m squared over 2. Now, from now on, we will be mainly dealing with Lagrangians, not the Hamiltonians. And once we have the Lagrangian, well, we didn't yet derive the equation of motion from the Lagrangian of this field theory. Now we will see how to derive it, but maybe we will leave it for next week. So next week we will start with the Lagrangian of any given Lagrangian. The first thing will be how do we derive the equation of motion given the Lagrangian. And then the quantization is actually, the quantization condition is just like imposing the commutators of P and Q. Here, in this case, once we know the Lagrangian, we can identify the corresponding momentum. Momentum and the coordinates, the commutation relation, will be just minus I h bar, Dirac delta x minus y. Now, this condition already quantizes the system. Once we have the classical Lagrangian, just like the classical Hamiltonian, I mean, remember how we quantized from the classical Hamiltonian. We started with the classical Hamiltonian and then just imposed the condition that P and Q are no longer numbers, but operators that satisfy this commutation relation. That was how we quantized a given Hamiltonian. Now we have the classical fields, which is essentially just a bunch of, I mean, we just assign a Hamiltonian at every point in space-time. So the coordinates are actually, we assign a different coordinate at every space-time, every point in space. And this eta is nothing but our generalized coordinate at every point. And there is a corresponding momenta to that generalized coordinate, which we call the pi. In this case, it will be a density. And the momenta and the coordinate, their commutation should be just, the quantization would be just imposing that this generalized coordinate and momenta, they are not functions, but they are operators whose commutation relation is given by this. And this should be enough for us to write down, solve the system. Just like we saw in the case of the simple harmonic oscillator, just knowing the commutation relation, it tells us what the energy eigenvalues and the properties of the energy eigenkets are. Questions?
Hocam şu en başta yazdığınız Hamiltonian'a bir
How far back
yani
up?
aslında aşağıdaki mesela şimdi bunu tam olarak nasıl yorumluyoruz? Yani şimdi Hamiltonian bana bir sistemin veya fiyatın enerjisini veriyor, değil mi?
Both the energy and how it evolves in time. You see?
Mesela ilk terimde bir noktasında bir enerji packet disappear ediyor. Sonra da tekrar yaratıyor.
Well, okay, so let me also define this operator, Ni. This is AI dagger AI. You see, we had defined these states n to be proportional to AI dagger acting on the vacuum n times. Now, if you act n, this operator n, ni, on this ket, it gives you that number. So basically, this operator as a whole is what is called the number operator. So this term basically counts how many packages I have. So every package has an energy epsilon prime. That is how I would rather interpret this term. Rather than annihilate the particle and create the particle at the same point, it just counts how many particles I have. Each one of them has the energy epsilon prime. So the total energy is the number times the epsilon. That's how I would interpret this one. This term is the kinetic energy, essentially. It's the motion. It will also contribute to the energy. And well, there are various terms in this expression if you open them up. It makes more sense to me to interpret this as a part of time evolution, like this term over here. So it annihilates a particle at the point I and creates it at the nearby point. Well, the difference between this term and this term is this term counts at every point. It doesn't change anything else. It doesn't move the particles around. It doesn't change the number of particles. It just counts. But this term, it has different effects. It moves the particles around. It can create two particles or annihilate two particles. So it's more complicated to interpret the second term. No, here there are no antiparticles. There's just a single type of particle. I don't need antiparticles to write field theory. Sorry. But if I want to write down a Lorentz invariant causal theory, I need to have antiparticles. But that will come later. Yes?
What bothers me here is that in order to define the particle that's moving to the right, we have to, by hand, put another particle that's moving to the left. Why do we need to have this sort of symmetry? I mean, can't we the particle that's moving to the right?
So, I mean, what you are saying is here if we have a theory that causes particles to move to the right, it's unavoidable to have motion towards the left.
Which is just momentum conservation.
It's not momentum conservation, but it's probably, I mean, I would say there's time reversal symmetry. Not really. For example, here I don't have any antiparticle, but I do have time reversal symmetry. Or in a sense, motion reversal symmetry.
Why I said momentum conservation was that initially.
Well, you see, momentum conservation is related with translational symmetry.
Yeah.
So you see, both of these terms, both of these Hamiltonians, they are translationally symmetric. Both of them should conserve momentum.
Yeah, but they're the same regarding to my question.
Yes. But you see, what I'm saying is the fact that if you have particles moving towards the right, you have to also have particles moving towards the left. It is not related with momentum conservation. That's what I'm saying. Momentum conservation is related with time translation symmetry only. If you have that, you automatically have momentum conservation. You see, if I didn't have the second term, if I ignore this term, then of course my Hamiltonian will not be Hermitian. That will be a problem, but I will still have momentum conservation. I will still have eigenstates with definite momentum. You see, here we had made this derivation. If I ignored one of those terms, the only thing that will be different will be, well, this term will be missing. But still there will be states of definite momenta, and their momenta will be conserved. But the energy eigenvalues will not be, let's say, how to say, the energy eigenvalues will not be real. The system will not be unitary. So this term is necessary for unitarity. So that's what forces me to include left movers if I have right movers. If I don't have if I don't have that, I don't have unitarity.
So if you quantize Geiger theory, we need to do it this way if want to impose dynamics into it.
No, we already quantized it.
Oh, yeah, but yes, so that's what I'm saying. You have to.
Sure.
How can we interpret Heidegger terms or A terms?
Heidegger terms. You see, what they will tell us, I mean, in this case, if you evolve your state will contain amplitudes which will have two more particles appearing spontaneously, let's say. They will be essentially vacuum fluctuations in the number, quantum fluctuations in the number. Of course, you can complain, how do we conserve energy then? So each of these packages have a fixed amount of energy, a minimum energy at least. So if you just create two particles out of nothing, well, the energy will be violated. There won't be energy conservation.
Don't we look at average energy?
No. Yes, energy conservation is an average law, let's say, approximate law in quantum mechanics. Energy conservation arises at a very long time. Remember the energy-time uncertainty relation. You can violate energy as long as that violation lasts short. That's for a very short amount of time. For example, in particle physics, we are looking at processes in which, let's say, an electron comes, it exchanges, it emits a W boson, becomes a neutrino. At the same time, a proton comes and it becomes a neutron. Sorry. We are looking at such processes. But if you consider the masses, mass of an electron is something like 0.51 MeV. Mass of the neutrino, well, we don't really know much, but it is less than 1 eV. And mass of the W is something around 80 GeV. So this is almost 90 times heavier than a proton itself. And the electron is 2,000 times lighter than the proton. But here we still have an electron emitting a W boson. Of course, energy is not conserved. But what counts here is, in the long term, you don't see the W boson. What you see is there is an electron, proton, they collide, and you end up having neutrino and neutron. Here there is energy conservation. Overall, there is energy conservation, but at intermediate state, you don't have energy conservation. So that those Heidegger A terms or AA terms, they don't conserve energy. Energy in the sense of energy of the non-interacting theory, let's say. Energy in the sense that energy, the sum of the energies of each individual packages. They don't conserve that energy, but if you look at any process in the long run, they will still conserve energy. So at an instant you have two excessive particles, well, soon they will just annihilate because of the AA term. Now let me give you another assignment. Well, we started with the annihilation creation operators, and we worked with them. We took their continuum limit, and afterwards we just take the real parts and imaginary parts and said that the real part is like just like the position, and the imaginary parts is like just like the momentum. Well, let's not introduce the creation, annihilation, and creation operators, but let's just stick with the harmonic oscillators. Let's imagine this system. You have many masses. They are attached to each other by strings of string constant k. And let me also assume that they are hung from a ceiling by ropes L. And this is G. For small oscillations, what is the Lagrangian of the system? And take the continuum limit. It's not quantum mechanics, it's just the classical limit. Of course, in this limit, for example, one thing you will need is m over L. Let's just call it rho. It's the mass density. As you take L goes to 0, m should also go to 0, such that rho is finite. And as L goes to 0, k will go to infinity, such that k times L, let's just give it some name, lambda, finite. Sorry, L, okay, let's change this from L to, okay, this is L. Let's call that capital L. And see what you should do for capital L. Capital L goes to what? Is it finite? Does it divert? Does it go to 0? So this is one homework. The other assignment was that was the other one that I said in the first hour. Anyway, okay, the normalization. Okay, so I will take that. And please send me your email addresses, especially if you are planning to continue, because I will put these in hour2 class, so I can add you in my hour2 class course webpage. And I will write these down so that you can download the homework from hour2 class. Start doing the homeworks now. I will collect them in 2 weeks. Not next week, but the following week. So that add drops will finish, and you will finally decide whether you will continue with this course or not. So see you around.